Thank you.
I think we'll move on now. And we've got Melanie, who's going to talk to us about internal wave-driven mixing.
Hi, everybody. My name is Melanie Rev. I'm currently working on a PhD at the University of British Columbia. And today I want to talk about some new results that my supervisor, Stephanie Waterman, and I have worked on this summer that involve multi-year mooring data to investigate the internal wave-driven mixing variability on highly resolved temporal scales. So just as a brief outline for the talk, I'll start by discussing some of the key elements that have motivated us to start looking at variability in mixing rates, and particularly the temporal variability of that mixing. I'll then describe the multi-year mooring data that we use in this study, as well as the basic details of our key method, which involve a fine-scale parameterization of turbulent dissipation. I'll then spend the remainder of the talk focusing on our key results, which involve large temporal variability, distinct geographic distributions, and cyclic variations. Finally, I'll finish with a brief summary along with some goals for the future. So, as we all know, mixing rates and their space-time variability have important impacts on the nutrient, salt, and heat fluxes, as well as water mass transformation rates. Unfortunately, large variability in these mixing rates present challenges in our efforts to characterize these properties, since they can obscure underlying patterns and significantly inhibit our ability to interpret limited and localized observations. So in particular, in some previous work involving a widespread CTD dataset throughout the Canadian Arctic, which we recently submitted to JGR, we found hints that really large local temporal variability appears to be a prominent feature of the mixing environment. For example, in a case study of 415 nearby profiles in the Amundsen Gulf, we found that even among these highly localized measurements, our estimates of wave-driven mixing still spanned upwards of 4 orders of magnitude. Additionally, we found that large episodic mixing events throughout our study domain appeared disproportionately important in contributing to rare but large upward turbulent heat fluxes out of the Atlantic water thermocline. So specifically, by using our estimated internal wave-driven mixing rates, we found that we used those to infer the associated heat flux, FH, and found that over half of the net integrated heat flux was generated by only 10% of all of our FH estimates. So given some of these hints, it appears that a robust characterization of this exceptionally large temporal variability is crucial to improving our understanding of the Arctic mixing environment. So in particular, this would help us improve our ability to identify long-term trends, allow us to more accurately account for the contributions of high-end outliers, and it would further help us gain insight into some of the underlying forcing mechanisms that are driving the observed mixing. So motivated by this need for a better characterization of the time variability of mixing rates, the big picture goal of our current work is to investigate how highly resolved time series of internal wave-driven dissipation and mixing rates vary in time from hourly to yearly timescales. And then we further compare how the patterns in these time series differ across distinct regions in the Canadian Arctic. To accomplish this goal, we've had the opportunity to investigate 2 highly resolved mooring time series in the Canadian Arctic, pictured here. So first, we have a 1-year time series in the Beaufort Sea from 2003 to 2004, which was collected as part of the Canadian Arctic Shelf Exchange Study. And then we also have 4 individual moorings in Nares Strait, which each operated continuously from 2003 to 2006 during the Canadian Archipelago through-flow study. So just as a simple model of what each of these moorings look like, the basic setup looks something like this, with an upward-looking ADCP and 2 or more CTD instruments. So using the ADCP data, we can obtain vertical profiles of horizontal velocity and thus shear, which capture approximately 100 meters of the water column in the Beaufort Sea and up to approximately 300 meters in Nares Strait. And each of these profiles were captured at 45-minute and 30-minute intervals, respectively. From the CTD instruments, we can use time series of temperature and salinity to provide an estimate of the average or background stratification. And then using these two ingredients, we can apply a fine-scale parameterization to obtain time series of the turbulent dissipation rate and the mixing rate. So just as a brief outline of this method, the basic theory involves ideas of the downscale spectral energy cascade from internal wave scales to turbulent microscales where dissipation and mixing actually occur. So essentially, it provides an estimate of the turbulent kinetic energy dissipation rate, epsilon, that we expect to result from internal wave breaking. So this parameter is a function of the shear variance integrated over internal wave scales. It's also a function of the background stratification and a number of empirical correction factors. So once we have epsilon, we can then obtain the internal wave-driven diffusivity, kappa, in the typical way by applying the Osborn relation. So using our time series of the vertical shear and the stratification that we extract from our Moraine data set, we're able to obtain over 10,000 estimates of epsilon and kappa over 1 year in the Beaufort Sea, and over 600,000 estimates over 3 years in the Nares Strait. So for the modelers in the room who can get millions of data points with the click of a button, this may not seem terribly exciting, but I think that the observationalists in the room will probably be with me in thinking that it's pretty cool. All right, so I want to spend the remainder of the talk highlighting our 3 key results that have come out of the analysis of these estimates of epsilon and kappa. But I'll just caveat quickly to say we're still in the preliminary stages of this analysis. So there's still a lot of work to be done, but these are some of the high-level features that have popped out so far. First, similar to the results of the CTD analysis in the Amundsen Gulf that I showed at the beginning of the talk, we find that at a fixed location in space, our estimates of epsilon and kappa span 4 to 6 orders of magnitude. So you can see that here in our estimates of the Beaufort Sea for both the dissipation rate and for the mixing rate. And this widespread is also evident in Nares Strait, but actually to an even larger degree here. However, despite these wide ranges, which you might imagine would make it difficult to distinguish patterns in different regions, we actually find that our estimates from the Beaufort Sea and from Nares Strait are actually characterized by clearly distinct distributions. So here you can see this in the geometric means of each of these distributions differ by nearly 2 orders of magnitude. And further, we also see no overlap between their respective standard deviations, which are shown by these dashed lines. And finally, the last point that I wanted to highlight today is that time series of our turbulent estimates show evidence of cyclic variations. For example, in this time series view of the dissipation rate, your eye can pick out this suggestion of a seasonal signal in epsilon, where epsilon is elevated in the summer and weakest in winter. And so this pattern is consistent with the seasonal cycle that we found from our CTD analysis in the upper water column, and it's also consistent with some previous work on internal wave amplitudes done by Haley Dosser and co-authors in 2016 that also reported elevated wave amplitudes in the summer. Next, if we zoom in on the high frequency components of this signal, then in spectral space, we also see some evidence of either a M2 semidiurnal tidal signal or a near inertial signal in this frequency domain. So there's still a lot of quantitative work to be done here, but we think that a more thorough investigation of this frequency content holds a lot of promise for providing insight into the underlying forcing mechanisms that may be modulating some of these temporal patterns. So just to summarize quickly, I want to recap the key take-home messages of what we've discovered in this work so far. First, we found that temporal variability at a fixed location spans 4 to 6 orders of magnitude. Second, despite these wide ranges, we still found that distinct distributions can exist in different regions. And finally, time series of our turbulent estimates show evidence of cyclic variations, certainly at the seasonal cycle scales, but we've also found hints that other frequencies may be important as well. So like I said, there's still a lot of work to be done here. So in terms of moving forward, some of the things that we're most interested in looking at next include a more thorough investigation of the frequency content of epsilon and kappa, which we hope will help us gain insight into the forcing mechanisms, like I said, as well as identifying the most important timescales. Additionally, it would be interesting to evaluate how environmental conditions, such as winds, tides, and sea ice cover, influence the observed variability. And then eventually, we also think it would be really interesting to explore the time variability of internal wave-driven heat fluxes that are associated with our estimated mixing rates. And so with that, I'll finish and just leave you with this very adorable photo of a polar bear. Thanks.
Okay, we have time for some questions.
Hey, in your time series, do you see any evidence of the presence of eddies in your, like, the moving observation?
I haven't looked for them yet. I don't know what I would be necessarily looking for. So we definitely haven't investigated it.
Because there have been some estimate for the mooring in the Canadian basin, and basically when you look at that, most of the variability, a large part of the variability comes from eddies passing by, and you end up with very elevated mixing in your eddies.
Right.
So I was wondering, and especially when in your mooring in the Beaufort Sea, I think you should get a lot of eddies there, and that's probably also explain why you get a wider distribution of mixing there.
Yeah, thank you for the suggestion. Basically, everything I've done, I showed. So it'll be interesting to look at some other things too. It's very new.
Can I ask a question?
Yeah.
I'm curious as to what sort of events, like temporally, are happening at the high and low end of when you see like these large diffusivities and low diffusivities. What's actually happening?
Yeah, so I'm not really sure yet. Even in that spectral space, like Tom mentioned, the near inertial signal and the tidal signal are right over top of each other. So just by looking at that, you can't really say. But I think based on a lot of the work that Tom has done with others, as well as some work that's been done in the Southern Ocean, there's evidence that the tidal influence can create bursts 3 to 4 orders of magnitude above the mean, is sort of encouraging that we think it's probably tidally related, but we haven't been able to prove that one way or the other. And yeah, we also found similar things in the CTD work that said that the winds weren't that important at depth. So it's kind of more evidence towards the tidal signal otherwise.
One last question? No? Okay.
Thanks very much.
So we'll move on to Ilker Fair, who is talking about variability and mixing of the Atlantic water boundary current around Svalbard.
Can you Does this work? Does this work?
That should work, yes.
Okay, great.